In this physics lesson, we'll be talking about electromagnetic induction. Previously, we have discussed magnetism, electromagnetism, and now we are doing electromagnetic induction. So these concepts are very related. So first of all, what is electromagnetic induction? So electromagnetic induction is a process of producing electricity or electromotive force when a wire is moved across a magnetic field. And it can also be done by pushing a magnet into a coiled wire. Previously, when we were talking about electromagnetism, we talked about motors, where we said we are producing a certain effect by pressing what? By pressing a current conductor between what? Between a magnetic field. And we are calling that as the magnetic effect. What was happening? The magnetic fields of the permanent magnets and that of the current conductor pressed between the permanent magnets, they were what? They were interacting, and that interaction caused the motor effect or the wire to rotate. So now, what electromagnetic induction does is just that it does the opposite of that. Whereas there we're using what? We're using the magnetic fields to produce what? To produce a force or a rotation effect. Whereas here we'll be using the same what? We'll be using the same magnetic field to produce current or to produce electromotive force. So, and this effect is called the generator effect. So to understand this better, let's have a look at two different experiments. Whereas we'll be inducing electromotive force in a wire by what? In two ways. Whereas the first way we'll be moving a wire across a magnetic field, or we'll be moving a magnet towards the what? Towards the wire. So let's start with inducing electromotive force by moving a wire across a magnetic field. So we can have a setup like this one, where you can have this is what? This is a conductor. So you should connect the conductor to what? To a galvanometer, or you can connect to an ammeter, but a galvanometer is the most required because we'll be using small magnets. So the kind we should be reduced to actually be small. So let's use a galvanometer. So we use a galvanometer and we press what? We'll press this conductor on a what? Between two permanent magnets of different polarities, so that there is a magnetic field around them. So what are we going to be doing to this one to induce current? Initially, if the conductor is still, the pointer will point at what? We point on the middle at 0. Right? But if you hold the conductor with your hands like these ones, then you push it upwards and downwards. You observe that if you push it upwards, the galvanometer will deflect to one side. If you are going to push it downwards, it will deflect to the opposite side. If you do the process like you do, moving it up, down, you observe that the galvanometer will be going either this way, then the other way, or this way, or this other way. So it will be deflecting. It will be like showing some other readings of showing that there is indeed current passing through the what? Passing through the conductor. So what does this mean to say that there is current passing through the conductor? It means to say that the wire has already electrons as we learned in metallic bonding. So what's needed is just that there is just need of a force to move these electrons to cause what? To cause current to flow in what? In the conductor. So what is happening here is just that the electromagnetic force is producing an electromotive force that is there to move the electrons, hence producing current. That's why we're having readings on the what? Readings on the ammeter. And again, let's look at this setup where, as we're saying, to induce electromotive force by moving a bar magnet in and out of what? Of a solenoid. So we all remember what a solenoid was. So here we're having what? We're having a current, we're having a conductor wound against what? Wound against the solenoid. Then it's also connected to what? To a resistive galvanometer. So here we're having what? We're having a permanent magnet. Here we're having the north pole, there we're having the south pole. So which means the magnetic field will be around this permanent magnet. So how will this magnetic field be arranged? It will be like this. So this will be the magnetic field, something like that. So they all strip from the north pole going to the south pole. That's how they will be like. So if you bring the permanent magnet, if you move it away from the conductor, you observe that the galvanometer will point at 0. There will be no readings. If you move the conductor towards the setup of the solenoid, you observe that the galvanometer, the point on the galvanometer will deflect to one side, and if you pull it away, it also deflect to another side. If you bring it in and out, rapidly, you observe that there will be what? There will be simultaneous changes on the pointer's deflections. So it will deflect to one side and go to the other side. If it cuts many wires, it will go to the other side. So what is actually happening here? You can see that you're having the magnetic fields there. Then you're having the wire. So what is happening is that, or what is needed for electromagnetic induction to take place, or electromotive force to be induced into the conductor, is that these magnetic field lines of the permanent magnets, they have to be cut by the conductor. So it's like the conductor should pass through the magnetic field lines, so that electromotive force is induced in them. So that is all about electromagnetic induction. Take note of that. The changing the direction of the movement of the wire changes the direction of the electromotive force. Therefore, the induced electromotive force is an alternating current. So, yeah, you might observe that we'll be using the terms induced alternating current, induced electromotive force. What is actually induced is the electromotive force, but the type of current which is produced is the alternating current. So, what does this electromotive force effect have? It has an effect on the current which should be produced. So, why is the current being produced is an alternating current? You can observe that in this setup, we're saying when you bring the magnet closer, the deflection. Let's say when you bring this one closer, the galvanometer is deflecting towards the positive side. If you bring it out, it's deflecting towards the negative side. So, which means the electromotive force which is being produced is what? Is changing. It's rising then falling. Rising, I mean, it's going to the negative, up to the negative. Falling is going what? It's going down to the negative. So, which means the induced electromotive force is what? Is alternating, so it changes. Therefore, the current should be produced also be what? It will be an alternating current. Then let's talk about how we can increase the induced electromotive force in the conductor. So how can we increase this one? Moving the wire first across the magnetic field, across the magnetic flux. So a magnetic flux is just the same as the magnetic field, and by using strong magnets, which means if you use strong magnets, the field lines, or the effect of the force, we say the field lines is just like a place where the magnetic effect will be felt like. So if you use strong magnets, it means they will have a strong magnetic field or magnetic flux. And here we're saying increasing the length of the wire in the magnet. So what will this effect have on the induced electromotive force? If we increase the length of the wire, it means that more of the magnetic field lines will be cut by this conductor. Hence, there will be more of the induced electromotive force which will be produced in the conductor. So if we increase the length, it means that more of the magnetic field lines will be cut. If you move the wire fast, it means that even if you are moving it fast, it means that more of the field lines are cut per second or per unit time. So the more the induced electromotive force. Now let's talk about the laws of electromagnetic induction. So what are some of these laws of the electromagnetic induction? So there are laws which governs the electromagnetic induction, whereas these laws will practically determine the induced electromotive force. So the first law is the Faraday's law, which states that the size of the induced electromotive force is directly proportional to the lead. Yeah, should be like not lead. Is directly proportional to the lead at which the magnetic field lines are cut by the conductor. So if this law practically means that the size of the induced electromotive force is directly proportional to the lead. So as we said earlier or previously, we say that if we move the conductor or the magnet fast, the size of the induced electromotive force will be more. So that's actually Faraday's law. Whereas if more of the field lines are cut per second or per unit time, it means that the more the induced electromotive force, or the more the size of the induced electromotive force. If less magnetic field lines are cut per unit time, that means there will be a small size of the induced electromotive force. And you also have another law, which is the Lenz's law. So the Lenz's law is there to govern the direction of the induced electromotive force or the induced current. So the Lenz's law states that an induced electromotive force always acts to oppose the cause. An induced electromotive force always acts to oppose the cause. So we can say an induced current always flow in a direction such that it opposes the change producing it. So this is another way of stating the law. So what happens is that when you bring a magnet towards the conductor, it's like the current will tend to flow away from that particular point, producing the electromotive force, causing the current to move. When you are moving the magnet away, the current will tend to follow the magnet. Let's look at this scenario by having a look at the diagram. Suppose we're moving a magnet towards the solenoid. So if you bring a magnet towards the solenoid, so the few lines are cut. So we are saying the induced current always flows in a direction such that it opposes the change producing it. So because the magnet is going in this direction, so it will be like the current will tend to run away from that point, whereas the field lines are being cut, or the change or the magnet which is producing the electromagnetic force. And if you try pulling the magnet out of the setup, it will be, you can observe the movement of the current. It's like it's going or it's acting to oppose the change producing it. So it's like it's going to the point where the magnet was being acting. So we can summarize this by saying that it says that an induced electromotive force always acts to oppose the cause. So here, what is the cause? The cause is the magnet. So if you bring the magnet close, it will be like the current will be running away from the magnet. If you pull it out, it will be like the current will be following the magnet. So that's all about the Lenz's law. So having a look at the introduction of electromagnetic induction and those laws, let's have a look at generators. So what are these generators? A generator is a machine which generates or produces electrical energy by rotating the coil across a magnetic field. So this is practically what we are just doing. But a generator is more sophisticated, whereas it's a machine which does all what we have discussed. So a generator is a machine which generates or produces electrical energy by rotating the coil across a magnetic field. So there are two main types of generators. We have AC generator and DC generator. So first, let's start having a look on the laws. So what are these laws used for? So these laws are there to determine the direction of the force, the direction of the current, and the direction of the magnetic field. So we have only one law which governs this. Previously we discussed Fleming's left hand law, which we are doing some other things different to this one. Right now having the Fleming's right hand law. So what does this one do? So this law, as I've said, is used for determining the direction of the magnetic field, induced current or EMF, and motion of the wire. So this is how we'll be using the Fleming's right hand law. So the first and the second finger of the left hand, they have to be placed perpendicular to each other, just like we are doing in the Fleming's right hand law. So if we do them in this way and press the second finger pointing the direction of current, it means that the first finger will point to the direction of the magnetic field, whereas the thumb will point to the direction of force. We can even use this law if you want that we want to determine that this wire or this particular conductor between the magnetic field line should be going in this direction. So you can practically use this law and align the magnets and even the conductor, so that the effect produced will be needed as you use for your specification. So if the first two fingers of the right hand are placed perpendicular to each other, and the second finger is pointing to the direction of current, it will mean that the first finger will point to the direction of the magnetic field, whereas the thumb will point to the direction of force. Now let's have a look at the AC generator. So what is the AC generator? It's a generator which produces alternating current. So we can have a setup like this one, whereas we can have two permanent magnets like this, then we have a coil arranged in this way, placed in what, placed between these two permanent magnets. Right here we're having slip links. So as you can see, the first part of this one is connected to what, is connected to the slip link, and this part is connected to, what, to the second second slip link. Then right there having the brushes, they're having the wires connected to what, connected to the bulb. So how does it work? So we're saying it has two slip links, whereby each carbon brush remains on the what, on the same link. So this carbon brush will remain on the same link when the coil is rotating without interchanging what, without interchanging positions. Thus these directions of the current in the coil changes after every half cycle. Suppose during the first half cycle this side was positive and this side was negative. So if the coil rotates, it means that this side will again become negative and this side will become positive. So the positive and negatives keeps on changing. So because they are changing, they are alternating each other. So the current which should be produced will be, it will be an alternating current. So what's there, or what's supposed to be done for the what, for the conductor to keep on rotating? So when the coil is rotated, so you have to rotate this one manually. So when this coil is rotated, it casts the magnetic field lines, and an electromotive force is what, is generated. So this electromotive force which is generated, it makes current to flow in the what, to flow in the conductor. So as the coil is rotating, each side travels repeatedly upwards and downwards. So the current also flows repeatedly, hence alternating current. Here by saying repeatedly is that when it's going on, when it's going upwards, let's take upwards as positive and the downwards as negative. So when it's going upwards, the current will rise. When it's going downwards, the current will fall. So it will be like the graph, even which will be produced by this, will be like it will rise, then it will fall. It will rise, then it will fall. So which means is what is changing. The maximum current is recorded when the coil is horizontal and carrying field lines at a fast what, at first lead. And the current is there when the coil is what, when the coil is vertical and cutting no lines. So when this coil is vertical, we will say that it's carrying no lines, as it's in the same what, same line as the what, as the magnetic field lines. So current is maximum when the what, when the coil is horizontal, when it's carrying one, when it's carrying many lines. So let's come again on how this one works. So when the coil is rotated, or is being rotated along the what, along the magnetic field lines, when it just cuts the what, cuts the magnetic field lines, electromotive force is induced inside the what, inside the conductor. So the electromagnetic field which is produced flows to what, flows through the conductor. But because this part are connected to the what, are connected to the what, to the slip links with no gap, and they keep on what, they keep on interchanging. Let's say this side is the one which is causing negative and this side is the one which is causing positive. So as you can see, this one is fixed on this one and this one is correct, is fixed to the what, to this slip link. So which means in the first rotation, when this part is positive and it has already that such that this part connected to this carbon brush, it has reached this point, it will again be, it will again be negative and this side will be positive. So which means to say that if this one is positive during the first half cycle, it will mean that this one will be negative, and in the next half cycle this one will be negative and this one will be positive. That's the alternating current which is being produced. So this is how the graph of the AC generator will be like. So it will rise, then it will fall. It will rise, then it will fall. So here is having what? It's having maximum positive amplitude. There is having maximum negative amplitude. Now let's have a look on the DC generator. So the DC generator also works on the same effects. You place the conductor between two permanent magnets. The only difference is that there we had what, we had slip links which didn't have a gap in the middle, whereas here we only have one split link, but the carbon brushes were again B2. So here we have a split link for a reason, also called as the commutator. So the setup will be like this, and we have the coil in this way. So it has one slip link where two carbon brushes are in contact, and these brushes are arranged in this particular way so that as the coil goes through the vertical position, the changeover of the contacts occurs from one half cycle of the what, of the split link to the other. So during the first half cycle, let's say this part was what, this part was positive and this part was negative, but because these ones they keep on changing on the what, on the middle, and they're not fixed. So which means when this wire is negative during the first half cycle, and it reaches the what? It reaches the contact, and by the moment it just touches this one, it will what? It will be positive, and this one will be negative. So it's like if this side is negative, it will remain negative. If this side is positive, it will remain what? It will remain positive. This is the reason. The reversing of the connections makes the current to flow in the same direction. Hence, the current produces the direct current, which means if this side is positive, this side will remain positive. If this side is negative, it will remain negative. And the opposite is true, which means if this side was negative, it will remain negative. And if this side was positive, it will still remain what? It will still remain positive. So that's how the DC generator works, and how the DC generator differs from the what? Differs from the AC generator. And this is the graph of the what? Of the DC generator and how it will look like. So since the current is direct, it only have what? It only have one direction. It will only be either the positive. It only have what? The graph only have positive amplitude or negative amplitude. So here we're only having positive amplitude only. As you can see, there is no negative amplitude. So this is during the first half cycle, the second half cycle. So this is how the what? How the graph will look like. The current will be direct. So for now, let's stop there and let us watch the next video talking about mutual induction and transformers.